Oh, let's close my camera.
Okay, close your camera, fine. So yeah, making my ninth grade 14-year-old student start doing linear algebra, that's definitely a good flex for my page. Um
Yeah.
um Wait, quick question, Ken, can you just give us an introduction? An intro,
Yep.
how old are you? How long have I been teaching you?
Okay, so I'm specifically 14 years. Oh, 15 years old actually this year, ninth grade, and wait, you've been teaching me for around 3 years, almost four now.
Awesome.
Close.
Thank you. And you went from what to what?
I went from like a fifth kind of 50 in like a situational problem to now like an 87 in situation problem.
Good. So, and your overall average is close to,
Close to 90, close to 90 now.
when was the last time you had an average below 90?
The last time it was nearly a couple months ago now, quite a while now.
But before that, so in total in the 4 years, how many 80s did you get?
It's been getting less and less. Now I've been, for instance, my quiz has been like overall is now 90, and so is my test and my exams. The overall is 90, and the only sector that I'm slightly weaker at is situational problem, which I am still actively improving as of current.
Awesome. Thank you. So yeah, that's just for all the other potential teachers. So let's get started. So how do we know that 0 and 1, that 0 is less than 1? So here's how I want you to think about it. If you have no apples and you have one apple, and I give you an apple,
Yes.
um, when you had no apples, do you have more apples after I gave you one, or when you had one apple?
Well, clearly, when I had one apple, I have more than when I had
Exactly.
no apple.
So the reason why we know that 0 is less than 1 is because of the value that 0 entails. Like what do we actually have in value terms before and after if we would do something such as addition, if we would do something as such as multiplication, if we were to subtract. So if you subtract from 0, you're going to get a much less smaller, more negative number than if you subtract from 1. Um, so yeah, that's basically how we start putting values and start placing values on a number line, right? That's super simple. That's what we've always been doing, right?
Right.
And this definition of q being rational numbers, being a fraction, follows the same. So if we had a denominator that is smaller, we know that the number is larger because we're dividing by parts. But if the denominator is large, then obviously the number will be smaller because then there are more people or things we're dividing that number on. Um, Fantastic, super simple definition that we understand. But when we start learning about axioms, here is how we know. So, for example, the additive identity, that's basically what we just used to understand that 0 is less than 1. Look at axiom 1.1.2. Okay. So if we add anything to 0, we just get an x, right? It doesn't, if you add something to 0, you're always going to get the same something back. Can you do that with 1? No. If
Yes.
you
Yes. By
if you do
extension, yes.
wait, if you were to do x plus 1, would you get x?
No, I would get x plus one because we don't know
Exactly.
what the value of x is. But since we're adding something to it, it would be like the original value of x, whatever it may be, was an additional one to it. So it
Exactly.
cannot be the same x value not there.
So this is basically what we were just doing. So x plus 0 is obviously less than x plus 1, clearly.
Yep.
Um so this is what the axioms do. So what's an axiom? Remember when we started, when we read about the elements? Remember
Yes.
that? So it had a
Yep.
bunch of propositions, right? So basically, those propositions are axioms. And basically, what an axiom is, they are self evident statements that are true. So we can prove that they are true. We proved it when we did the elements, when I showed you the propositions in the elements a
That was the
really
proof
long
work.
time ago. Don't worry about that. And basically, the reason why we're doing this is because we know in our world that we have an X and a Y, right?
Yes.
We can also have a Z, right?
Yes.
We could have even more dimensions. And when we have, so quick question, if quick physics question, So if something has magnitude but no direction, what's that called?
It's a vector.
No magnitude, magnitude, no direction.
Wait a minute. Wait, vectors when it does have a direction.
Exactly. Um, so actually, let's continue with that. It's a scalar if it doesn't. But yeah, vector. So a vector has magnitude and direction. And if we have a vector, basically we can have a space filled with vectors. So the reason why we're redefining all the algebra is because we want to make rules to have something called fields. Okay.
Yes.
And a field is where two or more axioms hold true. Okay.
All right.
So when we were doing, for example, a system of equations, if we would say x plus y is equal to 5, right? 2x plus 3y, let's say, is 21. Oh, this is 3y. And then we say x plus y plus z is, let's say, 15. We would solve the system of equations with our axioms and basically would get a value for x and y and z. The more variables we have, the more equations we're going to have, right?
That's logical. Yup.
So that's basically what we need, why we need linear algebra. So I didn't tell you before that this is the starting of or the intro for linear algebra. I just told you that we're going to redefine what we know about the real numbers. And the reason why we're redefining it is because we want to make algebra generalized. So you know how we add, subtract, exponential laws, all that stuff. We want to basically generalize